From Google, we have Miguel Guevara, who's a project manager, and also Bryant Gipson, who's an engineering manager.
Thank you, Gary, and thank you, everyone. We're very excited to be here today. And as Gary suggested, we'll talk to you about some of the things that we did with the recent mobility reports that we launched about a month ago. I'll basically give you an overview of the reports, and then Brian will talk to you a little bit about the journey that made it possible for us to produce these reports, and we'll share some key takeaways. For those of you who don't know it, I'll give you a small introduction to those reports. We released these mobility reports about a month ago. The reports were a response to the fast developing situation evolving around the world. A lot of regions and countries went into stay-at-home orders, and we were hearing from public officials that they needed a way to verify whether lockdowns were having the intended effect. The mobility reports try to answer that question. What I find novel about them is the way in which they weave privacy natively. This was the first Google product built with differential privacy from the ground up. Brian will talk later about some of the privacy aspects of it. This is what a mobility report looks like. They generally give an overview of the current state of mobility within a geographic boundary. This screenshot shows the report for Germany. The reports also contain information about different categories of interest, such as parks, groceries, retail, etc. There are some cases in which we provide more granular data. Here you can see data for German states. This data allows policymakers to observe trends over time and judge whether some of their policy measures are being effective. It is important to mention that there might be cases in which we don't have sufficient data and we omit data for those regions or categories. Before Brian jumps into the privacy description of DP, let me make some comments about the underlying data. Location history is part of our product suite in Geo, and it's available on Android and iOS phones. And in a nutshell, it helps users remember where they have been and give them personalized information such as better restaurant recommendations. From the privacy point of view, location history is a totally optional Google account feature. It is off by default and can be paused or unpaused at any time. And users can view, edit, and delete some or all of their data at any time in their timeline, as well as set up auto deletion after 3 to 18 months. If you're not familiar with the feature, this is how you can find it on your Google account. And in terms of the reports, some of the reports privacy aspects, we designed these reports to provide high utility and privacy using data processing libraries that meet specific differential privacy criteria to ensure that no individual can be identified by their location or movement. The insights are created with aggregated anonymized data sets from users who have turned on their location history setting, which, as I said before, is off by default. We took, as you probably all know, the additional step of using differential privacy to ensure that no one can be identified. And with this, I'll pass it over to Bryant.
Thanks, Miguel. Getting to the point where we could actually build a new product from the ground up with differential privacy was a long journey. And I'm going to talk about some of the pieces that went into building those. In particular, building strong foundations, building frameworks that were familiar to potential users, and then helping the users navigate that privacy, utility, accuracy frontier. So the differential privacy infrastructure starts with the foundational libraries. We started work in these about 3 years ago, and our vision was to be able to power differentially private use cases that primarily could accelerate developer velocity. A lot of times people are kind of trying to figure out whether they should even be interested in getting interested in a thing. And so they're really just in an experimental phase, and the ideation phase is really where differential privacy provides a great way of getting an idea of overall statistical trends and fitness for use, and allows developers to start guiding their path towards product development. So the foundational library that we use at Google is the same one that we published and open sourced so that others can reuse our work. For us, it's always been important to provide transparency around our implementation, and we hope that the folks on this call have had time to kind of poke around and look at the library. This was launched last year in C++, and just a couple of days ago, we also launched a Java version of this. I think in the cryptographic community, and I think everyone here would agree, you don't roll your own crypto. And this is exactly the same for differential privacy as well. You know, reusing hardened implementations that have many eyes, especially from the community, is a really good idea. The second step that we took was to build a SQL engine. And you might be wondering why we started here, given kind of the variety of developmental frameworks. And the answer is really just kind of a combination of a hunch and early demand. SQL continues to be a high productivity data analysis tool over large data sets. It's something that everybody's familiar with, even if it doesn't end up being the thing that drives the final product. So back in 2017, we sort of sensed that there was an increasing need to provide a privacy-preserving way of manipulating.
Brian, we can't hear you.
So next slide, Miguel, if you got it. So as you can imagine, SQL allows almost anything, right? A lot of implementations are actually Turing complete. So enforcing differential privacy while at the same time allowing non-experts to write SQL they're familiar with is a big challenge. In particular, when we're talking about differential privacy, we want to talk about events over an entire user, basically an entire user ID. And so that's one of the big challenges. The other challenge, of course, is changes in cardinality. You know, can I expand the number of contributions a user makes just by virtue of the query? Next slide, yeah. So, of course, the basis of differential privacy is really about quantifying the effect that a single user can have on output. So at heart, the differential private SQL really has to have the same property. So the first decision that we made was splitting SQL statements into sort of two parts. The first is transforms within the scope of a particular user, things that that user owns, for lack of a better word. And then a separate part of the query, which is statements that are made across the results of those individual transforms, across many users. More specifically, what this means practically is that we have a really generous kind of fully SQL compliant transform of a specific individual's data, including joins and custom functions, really unconstrained SQL, so long as it only occurs within the space of what a user owns. And then that gets passed off to that much more constrained set of cross-user transforms. And these transforms are based on the foundational libraries we mentioned earlier. They include all of the basic statistical functions, mean, median, percentile, etc., while forbidding certain types of joins. You know, finally, though, proving differentially private correctness is an essential part of the privacy engineer's mission. Ideally, they should be provably correct from the outset. Model checking provides a baseline level of confidence to the development process. So as part of the foundational libraries, we employ a stochastic So this next slide is an example of a differentially private query. You know, like we said at the beginning, user-centric design was a big component of it. I think, as everyone here knows, educating people on even what differential privacy means is already a challenge, and getting engineers to interact with it in a way that allows them to do their job is a big selling point of sort of usable DP. So we wanted to make sure that the user understands that they're performing a private operation. So we added the sort of syntactic sugar anonymization keyword. And then we give the users potentially the opportunity to tune some relevant privacy parameters such as epsilon. The query itself contains the anonymization functions, in this case, a count and an average. And then a configurable per record confidence interval is released as part of any aggregated result. Of course, the details of this are much bigger than what we had time for here, so you can check out the full details in our paper that was published and recently accepted at PETS this year. And with that, I will pass it back to Miguel.
Great, thank you, Bryant. One of the first applications for the infrastructure that Bryant described was a use case driven by social science. About 3 years ago, we wanted to measure the impact of Hurricane Maria and mobility patterns in Puerto Rico. We partnered with scientists and produced this mobility map that was used as a proxy to measure the impact on mobility in Puerto Rico after Hurricane Maria hit. Most recently, some of our colleagues published insights into human mobility using the foundational infrastructure that we've built and that Bryant described. One of the significant aspects of the journey that we have traversed is the utility privacy frontier. This is a question that we get very often from users, which is how will differential privacy affect my data or affect my analysis? And we've provided users with a couple of methods to try to understand that privacy utility frontier. First, this is one of the ways that we help users think about the utility privacy frontier. First, by plotting the theoretical information gained resulting from applying a specific epsilon. This allows us to make informed choices and allows users to make informed choices as part of a privacy review process. But it isn't intended to be a guaranteed statement about outcomes or privacy guarantees. Of course, we also provide in a lot of our suites confidence intervals for a lot of our statistical functions for users to understand what's the precise effect of DP on their data. We also help users produce private statistics that help people understand the consequences of their parameter choices. Our goal is to allow users to make informed decisions. We want to give users the power to choose an epsilon or play with an epsilon and delta so that they can see the specific effects that differential privacy is having on their data. In terms of lessons learned during this journey, I would say that perhaps the biggest lesson is that it takes time to build this sort of infrastructure. It took us about 3 years to get to this point. The second takeoff is that building it in a flexible way that can be used by different use cases pays off. When we were building this 3 years ago, we never imagined that a pandemic like COVID would hit. So being ready for this kind of use cases is critical. The third point is that putting an emphasis on the user is important. At the end of the day, the power of differential privacy, I think, only comes with exciting and cool use cases, and the users are the drivers of those use cases. And finally, explaining that privacy utility frontier is key to garner user support. Only when give users a notion of what's happening with their data, they get bought into the method and they're able to play with it and become active supporters of it. With that, I don't know if we have time for any questions.
So if you could ask one of the questions that came up, which is for the COVID regional mobility application, what's the privacy parameter? What's the value of epsilon that you used?
Yeah, we released a technical paper that can be found. I think it's linked in the blog, and it details the exact epsilon that we used.
But could you give us a feel for what it is?
I don't remember the exact number, so I don't want to give something incorrect. So I think it's good to point to the paper.
In my experience, everybody knows epsilon except the person using it, or the reverse. In any event, so we have another minute. There's quite a lot of people are interested in that. So perhaps you could post that paper so that other people could find it. I think that would really be great. There's another question from Claire Bowen, which says there was some sound loss while you were talking, so it was clear some of these things, but I'm unsure what each of those parameters listed represents, such as K. Also, could you clarify? Well, same thing. What is the total up? So if you could explain what the other parameters are, I think that would be helpful to us.
Brian, do you want to take it?
Yeah, so basically we've got this in kind of a configurable mode, and I don't know if I can exactly say that the script that you saw there on screen was 100% exactly the same as what someone would be interacting with. But in general, you know, the thing that we want to guarantee is epsilon delta. And so those would be the sort of two primary parameters. If you read the differential privacy paper at Popets, we have a few other sort of more esoteric things that, such as tau and sort of partition limitations that are completely irrelevant and inscrutable to most people, and so they're left as defaults, but they are also configurable. So I guess short answer is every parameter that we outlined in the paper is configurable there.